and I'm so sorry for the technical troubles, but I'll try to keep us on time. Very excited to be sharing today about quantum. I'll start off with a brief introduction for those who are new to the space, and then I'll move on to all the exciting new developments that's been happening throughout quantum computing. Especially since 2016, we've put a real quantum hardware on the cloud for everyone to access. And then I'll be talking a bit more about our roadmap towards the future, as well as the ecosystem we're building to prepare the industry and enterprises towards this era of quantum advantage. And hopefully by the end of the session, it will give you a good insight of what quantum computing is. So yeah, there are many problems in the world within business, science, and our society. And we've always only just harnessed classical computing to solve some of these very hard problems. But there are still some problems that are beyond the resources that we have today to be able to solve. So we're now in an era where there's a new and more advanced type of computation with the opportunity to actually work on these problems and be able to solve them someday. So as you can see on the screen here, these problems includes, say take agriculture, for example, an estimate of 1 to 2% of our world's energy consumption is actually put into manufacturing fertilizers. And we are now talking about if we're able to look into how to create better and cheaper fertilizers and reducing the use of natural gases for the production of ammonia for fertilizers, for example, creating new catalysts, looking at new catalysts, or even talking about, whether we can get a better view of what's actually happening within different markets in financial markets to do risk assessments much more accurately, hedge fund investments, and even our retirement funds. And of course, with today's quantum computing computation power, right now, really, like we're in the midst of a pandemic, right? We cannot help with COVID right now, but all the work that we're putting in that we do with chemistry has the promise of ultimately allowing us to, find out what sort of drugs there can be in the future on a quantum computer instead of just doing in the labs as we do today. So looking at this chart, you'll be thinking, why do we need quantum computers, right? We already have the computers that we have today, and there's a lot of things that we can do with even today's supercomputers. So like reading emails, checking your phones every day. These are current computation power that can address things that we do today. But there are still some harder problems like factorization of very large numbers, problems that we think that even with today's computation power, we might be able to solve, but it might take a very long time or even beyond the resources that we have today. So we're looking at quantum to be able to not only just speed up the type of problems that we have today, but also solve the problems that we never thought that we'll be able to look into. For example, making more efficient lithium batteries. We're currently at a point where now we're working towards sustainability. We want to make it less expensive and even less dangerous, right? So we need to understand how these reactions happen and discover new molecules that can be used, right? And these are problems that we're unable to solve today, but with quantum computing, we are able to explore this space where the problem becomes really large and doesn't have enough resource to solve and look into. And some of the near-term quantum applications that we're looking at, and as you can see on the screen here, is first of all, because nature is truly quantum, right? Everything is quantum mechanical. We understand that we need quantum mechanics to make things work. And of course, simulating quantum systems is one of the very near-term applications that we can use. So as I talked about earlier, we can look into understanding the reactions, discovering new molecules, for drug discovery, so quantum chemistry, for example, and of course AI. We can also look into quantum AI, building better models for fraud detection, and of course optimization problems. So the traveling salesman's problem, finding the most fastest way to do things or the most efficient way to do things with the least cost. So these are generally some of the near-term applications that we're looking at. And if you compare where we are right now, you can see on the left is when we were starting to just use our computers, right? And in today's world, you'll never realize how important a computer may be to you. And this is exactly where we are at for quantum computing. We're at the era where we're already making use of a quantum computer, but it is still not at a stage where you can see an advantage over the computers that we have today. So referring to what I was talking about earlier, there are problems that we think we can solve with a quantum computer, but we are still at the stage where we're developing a quantum computer that is powerful enough with the computation power that will allow you to harness that power and solve problems that we cannot solve today. So tying back to classical, where we all understand, we always store information in bits, right? And we have always just used bits to, and if you understand bits is you can only do work one step at a time. But with quantum, this is where we're going to introduce qubits to you, if you don't already know, but if you know it, it's going to be really quick. Sorry, the next slide. So we're talking about quantum bits, and this is where we utilize quantum features like superposition and entanglement to be able to tap into the computational power that a quantum computer may have. So this is, imagine when you're spinning a coin, right? For a classical example, you are flipping the coin. You are just either finding a solution, whether it's heads or tails when you flip the coin. But when you look into how you can utilize a quantum qubit, when you spin a coin, all your problems can be mapped on that spinning coin, and the way that you compute or map your problem onto that quantum system will be when the coin is spinning instead of just flipping heads or tails. So that is how you can imagine the power of a qubit as compared to bits, where I will talk about later, as well as how you can see the comparison between bits and qubits and how much more power there will be in a quantum bit as compared to a classical bit. And of course, yeah, so here's the comparison that you can see with just 2 qubits. So to put into perspective, since 2016, we've put a 5-qubit quantum computer, real quantum computer, on the cloud for access. So just look at this chart, and you can see on the left, with just 2 qubits, you can represent 512 bits, right? So as you can see, as the qubits scale up, it's not just, say, doubling the number of bits. It's actually increasing to the point where if the moment you reach 160 qubits, for example, you already surpass all the atoms in the universe, right? Or on Earth. And this shows how that even with like the resources that we have today, you're not able to harness the computational power to be able to solve the problems that you have now. And this chart really shows that when we reach the level of, when we have the quantum hardware to be able to support, this is when all your problems that you're mapping into will be able to harness this computational power and be able to solve with just that number of qubits, right? So talking about this, when we talk about classical, we are already at the stage where we're no longer able to harness like exponential computing power. But if you look on the right, we're not just increasing the qubits on a quantum computer, we're also talking about how much power or how much can you measure out of a quantum system, right? So this is where we introduce a metric called quantum volume to be able to take into account not just the number of qubits that you put on a quantum system, because the systems that we have today are still very noisy, and there really is not much advantage over classical. But we're building towards where we can harness that computational power by taking quantum volume into consideration. So This is where we have been doubling our quantum volume every year, ever since we introduced our first quantum device, and we've reached a quantum volume of 128. So this shows that you are able to map a larger problem onto your quantum device as the quantum device and quantum hardware has an increasing quantum volume. So here's just a very quick chart of what it looks like on a quantum chip. You have the bus resonators where you're able to control your electronics with microwaves, and this is how you actually send in microwave electronics to the quantum chip to be able to process the problem that you put in. And you can see here on the chart, those are the qubits. And this is the only thing quantum about the whole quantum computer, which is put into a really cold fridge at sub-zero temperatures that's colder than space to be able to tap into the quantum mechanical features that, that only occurs in very cold temperatures. So moving on, so that's a very quick introduction to the quantum hardware itself. Here's the roadmap that we announced in September last year. And this is our vision for the development of the future of our hardware that will bring us towards quantum advantage. And this is done by building and advancing the technology of our quantum processors to be able to provide the computation, like I said earlier, and capabilities to solve problems at a larger and more practical scale. So you can see here, we are planning every year from 2019. That's what our Falcon, the one that we showed earlier, the quantum volume of 64. And towards 2023, we are looking at building 1,000 qubit quantum processor to be able to implement something that's more practical. And if you've all heard of this quantum error correction, not just building and adding qubits to the hardware itself, but also building one that has the quantum volume to support and implement circuits that will be able to be more practical, of more practical use. And this is a, this is a photo of showing you guys that quantum computing is no longer just in the lab. And this is something that we've designed called Quantum System 1 that we brought out of the lab into one of the quantum data centers. It's no longer just a research thing. It is actually possible to be able to be in a data center of the future. So here's a photo of one of our labs. This is a dilution fridge, which I was talking about earlier. For you to tap into the quantum chip of the entire quantum computer, you have to keep it at a really cold temperature to be able to tap into the quantum computing features, quantum mechanical features. And here you can see we're building a fridge that will be able to have inputs both at the top and the bottom. And this will be housing, the fridge that we're building will be housing the 1,000 qubit processor that I was talking about earlier. And also the ones, the future machines that will bring us towards 1 million qubits and beyond. So far, I just want to pause here for a moment and just recap so that I want you to have a sense that quantum computing will not replace classical computing. It is there are still problems that will need classical computing for, but of course we have to understand that quantum computing will be able to harness things that we're not able to solve in today's computing resources. We will not need a new type of cloud, apps, or any new programming language. And we'll just be able to infuse quantum computing into the cloud-based physical and software infrastructure that we have as of today. Yeah. So if we're running short of time, maybe I'll just ask, sorry, do I still have time until 4:15, or are we wrapping off soon?
Yeah, you could be a bit late, around 5 minutes. Yeah.
Okay, sure. So I'm so sorry. So on this slide, it's really just to showcase some of the applications that we've been working on with research as well as our network partners. So for example, here you can see for quantum simulation, we've been working with Samsung for entanglement dynamics on our quantum systems, linear systems. So with JP Morgan, we're working on option pricing using quantum computers, the real quantum devices. And we're also working with labs like MIT and Berkeley labs to be able to simulate some of the heavier ions of collisions, yeah, to be able to understand the properties better. So, okay, so here's the exciting part actually. Here's what I want to share with you guys. It's our newer developments that we've just announced. So Kisket Runtime is something that we're building and going to be announcing soon. And we want to get to the point where domain experts won't need to have a degree or a PhD in physics or maths or computer science, and just be able to take their data and to connect it to the quantum cloud, right? That's where we want to get towards. And we want to make the quantum service available and very seamlessly so that you won't realize that you're using a quantum computer. So Kisket Runtime is something that we're going to be introducing. And sorry, the next slide. And here you can see like we are developing the entire service so that developers will not need to learn something that they don't already know. We'll be using the same tools, the same programming language, and even the same code that you can just extend upon so that, really domain experts can tap into using the quantum device itself. Yeah, so here's just a very quick overview on the developers that we've already hired, the engineers and scientists that are already working on this, is that we have kernel developers who are looking into using and maximizing the performance of the quantum chips itself, and how the hardware runs and uses these tools, right? Okay, it's fine. We have so we have also the algorithm developers who are using a lower level tool to create the quantum algorithms to be able to incorporate the quantum and classical algorithms. And we also have model developers who are domain experts, but they also know how to use the compute infrastructure. So they can actually translate these problems from their domain, any industry at all, into algorithms that can be used to solve these sort of problems. And to make this even more relevant in industry, so these are the three main dimensions that we look at when we're considering how to improve quantum over the next few years, right? The quality, it's about the quantum system itself, not just the hardware, but we're talking about the entire stack, the software, the quantum volume, everything that's involved in the system to make it, to be able to harness the computational power. The capacity, how fast these circuits can actually run on the systems. So we use superconducting technology, which we can see on the roadmap. We've been scaling. This is where we're able to scale not just with more number of qubits, but with quality, and increase the rate at which we are able to run the circuits on. And these are available on all the multiple systems of our cloud. Sorry, just back again, real quick. And the last one is the variety, is the type of algorithms that you can be that can be applied to the hardware that we have. We want to make it possible for both classical operations and quantum circuits to be able to integrate together on a system. So another thing that we're introducing are dynamic circuits. We want to bring whatever you code closer to the quantum system so that it will be faster and we'll be able to do more and implement more algorithms with fewer quantum resources. So we can combine them. What we want to do when we introduce dynamic circuit is to be able for you to speed up all your processes. And allow you to be able to do more with a fewer number of circuits. And another really important highlight is that we are also introducing mid-circuit measurement, which means that you are able to run your entire circuit and be able to find out mid-circuit. You don't have to wait until your full iterations to be running. If you already know the outcome that you want, you can actually stop mid-circuit to be able to do a readout, and then depending on the readout, either continue or work further on your on the iterations. So this is a very significant development that we've put on the hardware itself to be able to even work towards quantum error correction. So here's the development roadmap. You can see the entire development roadmap from the hardware to the software to the libraries that we're building. So we explained the circuits that we've already built, the Kisket Runtime that we're introducing later this year, the dynamic circuits that are bringing the quantum systems closer to what you're coding so that you can cut down the number of the runtime, as well as the libraries that we'll be introducing. So the circuit libraries, if you already know Kisket, we'll have a workshop later after this talk, which Junyet will be carrying out. And the advanced control systems is so that when we build a system that is large enough, we need to be able to integrate it with the classical systems. And we're looking at, we need the controls to be able to use the functionalities to combine high performance computing with quantum processors itself. So not just having the quantum systems close to you, but we need a high-speed channel to be able to connect both the fastest classical computers with the quantum computers. Yes, so with that, I just want to recap that this year with the developments, we're introducing Kisket Runtime. You'll be able to run your iterations and applications faster, and that will really save you a lot of time when you're looking through use cases on what you want to build. Dynamic circuits, again, improving accuracy and resources, reducing the resources that you need to be able to compute. And the Kisket application modules that our team has built for the services to allow a seamless connection. So like I said earlier, we want the domain experts to be able to just put the data onto the cloud without needing a PhD or any technical expertise. So this is what we've introduced and what we're going to be introducing throughout the next few years.
Yeah, thank you very much.
Yeah.
Yeah, that's